Okay, thank you for your introduction. Hello, everyone. I'm Yongwon Shin, a PhD student at Postech in South Korea. Today, I'm excited to present our work, Autotuning Tensor Programs for Processing-in-DRAM. This is joint work with my co-first author, Dookyung Kang at Seoul National University. Modern computing systems are constantly evolving to tackle the growing gap between the computing speed and memory performance. At the same time, today's applications like LLM inference and data analytics are increasingly bandwidth hungry, making the memory the real performance bottleneck. In an effort to address the challenge, a paradigm shift is happening in architecture design toward moving computations closer to and inside the memory to eliminate the memory bottleneck altogether. Processing in memory, or DRAM PIM, embodies this shift by integrating computing units directly inside the memory. This allows data to be processed where it is stored, reducing costly data movement. Major vendors have released various DRAM chip products and prototypes. For example, OMMEM uses general-purpose cores, and SK Hynix and Samsung adopt specialized logic in their designs. These products show that DRAM PIM is no longer just a concept, it's being deployed. However, for emerging hardware to be adopted and widely used, programmable software stacks are crucial. But developing software stacks is always a tough job, and it's no exception for the DRAM PIM. Since current DRAM PIM stacks are still in early and experimental phase, if you want to run a specific workload, you basically have two options. First, use hand-tuned libraries built for a specific workload. Second, dive into a low-level programming model and write everything yourself. These two options have three problems. First, both options are hard to extend or scale. Each new workload still needs substantial effort with low-level programming model. Second, both methods often show suboptimal performance. Libraries don't adapt well to diverse input shapes, and manual tuning requires trial and error over vast search states, often leading to poor results. Lastly, unlike traditional processors, developers must deal with PIM-specific traits, like limited compute power. Current libraries often miss these optimization opportunities too. Our key insight addressing these limitations in the current software stacks is providing an expressive, extensible, high-level abstraction layers. Tensor IR is a natural fit as tensor computations are among the key operations accelerated on PIM hardware. Although the concept of adopting tensor-level IRs for PIM has been proposed previously, our goal is to fully automate code generation and optimizations using tensor-level IR. First, it enables schedule-based auto-tuning. Using just a few lines of code and simple scheduling rules, it can capture powerful optimizations. Second, tensor-level IR enables automatic code generation for both host code and kernel code. It also allows us to apply optimizations specific to PIM hardware traits while preserving high-level semantics needed to ensure correctness and safety. To this end, we propose ATiM, a search-based optimizing tensor compiler. ATiM supports fully automated code generation, PIM-aware optimization, and auto-tuning. Our goal is to advance DRAM PIM programmability and to enable streamlined optimizations of both host and kernel code. Our ATiM achieves up to 6.2 times speedup on benchmark kernels and 8.3 times speedup on the core operations of GPT-J layers compared to hand-tuned libraries and existing frameworks. That was the introduction and motivation. Next, I will explain a few key concepts. Let's first take a look at the OMMEM architecture of the DRAM PIM system we target. OMMEM consists of a host CPU, standard DRAM, and PIM-enabled memory. Each bank in PIM-enabled memory has its own data processing unit or DPU. This allows us to distribute work across banks, enabling true bank-level parallelism. Within each DPU, OMMEM uses multiple threads called tasklets to further parallelize the computation. And before computation, data must be staged from the main memory RMEM to the fast scratchpad memory WRAM. In addition, all data transfers between the DPUs and host CPU must pass through the host CPU. This off-chip communication is costly, so minimizing data transfer is critical for performance. Next, let me introduce Tensor IR. Tensor IR is a core IR for compiling deep learning models. It acts as a bridge between the various frameworks and tensor expressions down to low-level code for different hardware and backends. It preserves tensor-level semantics for high-level optimization and allows rolling to loop-based code for efficient hardware code generation. We have extended this pipeline to support DRAM PIM like unmem. One of the key features of TensorIR is schedule primitives. These primitives abstract how code should be executed at a high level, such as tiling for locality, parallelizing operations, or managing data caching. This makes it much easier to achieve high performance on hardware without handcrafting low-level code. For example, schedule primitives can improve locality through tiling by splitting tensors and setting the tile order. And data caching can be controlled with cache-related primitives. Also, thread-level parallelism can be specified by parallelizing loops. Next, these schedule primitives are lowered to loop-based code. This enables fine-grained, hardware-aware optimizations and automatic code generation. Lastly, TVM provides auto-tuning support for TensorIR. The auto-tuner performs iterative search-based optimization using cost model. Now I will give an overview of ATiM. As you can see, ATiM directly addresses the three challenges I mentioned earlier. ATiM is built on top of TVM and has three main components: sketch generation, balanced evolutionary search, and TIR lowering and optimization passes. First, TIR code is transformed into code templates called sketches. Then tunable parameters are sampled for auto-tuning. Second, balanced evolutionary search uses TVM's cost model to pick the best schedules. We also fix candidate imbalance problem for efficient search on unmem. Next, promising schedules are lower than optimized for unmem. The compiled modules are run on unmem, and measured latency is fed back to update the cost model. Finally, after tuning, the best module is lowered and optimized again to generate the final binary. Now I will show how ATiM performs search-based code generation using TensorIR. ATiM fully automates the entire PIM programming and optimization workflow using schedule primitives. It follows a standardized code generation process for DRAM PIM. First, the host distributes the data across DPUs and coordinates how the result will be combined. Next, each DPU processes each assigned workload as efficiently as possible through various optimizations such as tiling. Finally, the results from all DPUs are gathered and post-processed at the host site. ATiM expresses and optimizes the entire process using schedule primitives. How tensor data is divided across DPUs greatly impacts DPU-level parallelism and data movement. ATiM controls how the data is split, choosing the tiling dimension for efficient data movement and parallelism over the inter-DPU level using the split primitive. And ATiM can assign each tile to a DPU in any desired order by combining reorder and bind primitives. For reduction workloads, ATiM can optionally perform hierarchical reduction, first computing partial result on the DPUs, then aggregating the final result on the host side. This approach has a trade-off. It reduces input data movement, but increases output data and requires extra reduction cost at the host side. To make each DPU run efficiently, it's important to ensure good data locality and parallel execution across tasklets. This optimization starts with multi-level tiling, which divides the tensor to improve data locality. It also enables tasklet-level parallelism by assigning loop levels to tasklets by using the bind primitives. A DPU must load data into WRAM before computation, and when this happens can greatly affect performance. ATiM uses cache-related primitives to optimize these by assigning caching locations to specific tiling levels and scheduling data transfers between MRAM and WRAM. Lastly, when hierarchical reduction is used, host-side post-processing completes the final reduction. This step can be parallelized with schedule primitives too. Now I'm going to explain TIR lowering and optimization passes starting from the address calculation. Address calculation is needed because each DPU has a separate address space in unmem. So ATiM needs to calculate per DPU offsets from the global host address. ATiM first identifies WRAM access points to and from WRAM. At this point, because MRAM uses global host addresses while WRAM uses local address for each DPUs, ATiM can calculate how each global address should be translated into the corresponding local address at compile time. So data transfer code can be generated using this address mapping by placing data transfer intrinsics at the WRAM caching location. However, this code calls the data transfer intrinsics too frequently for every data element. ATiM optimizes this by leveraging bulk and bank parallel data transfer functionalities for efficient data movement. First, the current intrinsic transfers data one element at a time, which incurs high latency. So ATiM coalesces contiguous data accesses into a single data chunk by leveraging bulk transfer functionality. Moreover, as UNMEM supports a bank parallel data transfer API, ATiM substitutes the single bank transfer API with its parallel version after recognizing loops bound to banks. Now, I will show how balanced evolutionary search improves TVM's autotuning process for UNMEM. Here is a quick overview of the autotuning process. First, candidates are sampled from sketches, and they are evolved through evolutionary search. Lastly, for the next tuning iteration, top K candidates are selected from the database. On UNMEM, we observe that the default TVM autotuner struggles to tune both host and kernel parameters efficiently due to complex and larger search space than the CPU. Because there are so many candidates, standard epsilon greedy and top K selection don't explore enough in early iterations. This causes the search to quickly focus on one group, even if better options exist, highlighting the need for stronger exploration. So ATiM proposes two mechanisms. First, ATiM uses adaptive epsilon greedy, starting from high exploration and gradually reducing epsilon to balance candidate selection. Second, during early iterations, ATiM ensures candidates are evenly sampled from all groups in the database. Now I will present PIM-aware optimizations that efficiently handle boundary conditions on UNMEM hardware. When the input tensor shape does not match the model's expected shape, extra boundary checks are required to prevent out-of-bounds access. CPUs and GPUs have advanced latency hiding logic, so branch checks can hardly impact their performance. But UNMEM doesn't have this logic and has limited compute power, so frequent branch checks can slow it down much more. As shown here, reducing boundary checks can lower latency by up to 19% on UNMEM, while the same optimizations makes little difference on CPUs and GPUs. ATiM leverages TIR's high-level semantics to safely reduce boundary checks, something low-level compilation like LLVM cannot guarantee. First, DMA-aware boundary check elimination removes checks and replaces the loop with a DMA call for efficient MRAM to WRAM transfer. This is safe because MRAM are locally padded and remaining checks are repeated later in the computation statement. Second, ATiM can remove boundary checks by merging them into the loop bounds. This is possible when conditions can intersect with loop bound conditions by solving linear inequalities, and the loop is perfectly nested. Lastly, ATiM applies invariant branch hoisting by moving boundary checks above MRAM reads based on buffer usage analysis. This optimization requires high-level semantics because low-level memory operations would otherwise prevent safe hoisting. Now I will show evaluation results. We evaluated ATiM on 7 tensor algebra operations and 2 memory-bound operations on GPT-J models. We compared 5 setups. Prim and simple prim are existing prior work, and simple search, we extend prim with a larger search space. CPU auto-tuned is CPU version auto-tuned with TVM. Lastly, ATiM is our proposed system. Our goal is to see if ATiM's automated code generation and optimizations can outperform existing libraries and frameworks and CPU. This graph shows MTV and GMV latencies compared to prim. ATiM achieves up to 6.2 times speedup over prim and 5.8 times speedup over prim search. This is mainly due to decreased input data movement by 2D tiling with hierarchical reduction. The auto-tuned caching sizes are also affected by, since it is very hard to find by hand. On GPT-J, ATiM outperforms Prim by 5.7% on average for MMTV, reducing 11.7% on average for single batch scenarios. These gains come from more efficient caching strategies and increased DPU-level parallelism for single batches using 2D tiling. For MTV, ATiM achieves up to 6.6 times speed up across all kernels in GPT-J's 30 billion. ATiM consistently outperforms CPU, achieving up to 23 times speed up for tensors larger than 64 megabyte. This is because ATiM performs in-place parallel computation across DPUs, removing significant data movement during computation. ATiM's PIM-aware optimizations deliver up to 14.7% speed up on various MTV input shapes. DME-aware boundary check elimination gives the largest gain. And loop-bound tightening and invariant branch hoisting are also effective, especially for misaligned inputs. Our balanced evolutionary search improves auto-tuning process by 21%. Combining balanced sampling with adaptive epsilon greedy is critical to avoid suboptimal performance. In summary, ATiM enables search-based code generation for PIM systems, proposes PIM-aware optimizations that are effective for PIM hardware without complex hardware logic, and improves auto-tuning process by balanced evolutionary search. As a result, ATiM enables end-to-end search-based code generation for DRAM-centric PIM systems, including both host and kernel code, and shows a strong potential as a practical tensor compiler for diverse DRAM PIM architectures, outperforming existing libraries and frameworks. Thank you for attending my presentation.
Thank you. We have time for questions.